Good evening, everyone. It is with great honor and enthusiasm that I welcome you all to the inaugural ceremony of ATAL 6-day online faculty development program on the impact of inverter-based resources in the power system, organized by Department of Electrical and Electronics Engineering, ACGCET, Karaikudi, and sponsored by ATAL Academy. This FTP aims to provide a platform to faculty members to enhance their knowledge and skills in the inverter-based power system, a crucial area in transition towards sustainable energy. We are privileged to have distinguished personalities with us today who have played a pivotal role in making this FDP possible.
Let us start the inauguration by Tamil Thai Valthu, followed by Vallal Valthu.
நீராறும் கடலுடுத்த நிலமடந்து கெழிலொழுகும் சீராறும் வதனமென திகழ்வரத கண்டமிதில் தெக்கணமும் அது சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே உன் சீரிழமை திடம் வியந்து செயல் மறந்து வாழ்த்ததுமே
கோடி கொடுத்த குடைஞன் குடியிருந்த வீடும் கொடுத்த விடுச்செல்வன் தேடியும் அள்ளி கொடுத்த அறிவூட்டும் வெள்ளி விளக்கே விளக்கே
கொடுத்த அழகன்
முன்பெரும் தவத்தால் தோன்றி முயன்றமை காக்கும் வள்ளல் அறம் பழிப்போ
Now, to formally welcome our esteemed guests and participants, I invite Dr. K. Padmanabhan, Assistant Professor, Department of EEE, ACGCET, to deliver the welcome address.
Our beloved Principal, Dr. K. Bhaskaran sir, our beloved co-coordinator, Mr. V. Pradeep sir, and my dear participants, good evening everyone. I welcome our Principal, Dr. K. Bhaskaran sir, Professor and Head of the Department to this ATAL online 6-day FDP, impact of inverter-based resources in the power system. Actually, without our principal sir, we wouldn't have applied this proposal. During each and every department meeting, he insists us and encourages us to apply for this, to apply for any proposal or FTP. Apart from teaching learning, you guys have to apply for proposals like that. He keep on insists and encourages. So because of that encouragement only, we have applied for this ATAL FDP. So thank you, sir, for encouraging us to apply for proposals. And then it is our honor to welcome you again for this FDP, sir. I welcome our co-coordinator, Mr. V. Pradeep, sir, who is the starting point of this FDP. He only started the conversation like, Padhu sir, let's apply for ATAL FDP. Even the title of this FDP, he only chose it. So without him, this wouldn't have started. So I welcome you, Mr. Pradeep, sir. It is an honor to welcome you. And last but not the least, I welcome all the participants who are the soul of this FDP. I welcome you with a thank you because you guys have given the precious evening time of an entire week in your life, trusting us like we will give a worthy content to you. We will not let you down. Definitely the content is going to be very good, which will definitely help you in future research. So regarding the participants, we have participants from Jammu and Kashmir as well as from Kanyakumari, and around from 13 different states we have participants. So it is an honor and a privilege to tell that ours is a pan-Indian FDP, and I welcome you all again. Now I invite our principal, head of the department triple, Dr. K. Bhaskaran sir, to give presidential address. Thank you.
Thank you, sir, for your aspiring words and profound wisdom. Next, we are honored to have with us a visionary leader whose guidance has been instrumental in shaping academic excellence at ACGCET. It is my privilege to invite Dr. K. Bhaskaran, Principal of ACGCET and Professor and Head of the Department of EEE, to deliver the presidential address.
Good evening all. We are delighted to meet you all through this ATAL online 6 days faculty development program on impact of inverter-based resources in power system. Our institution, that is Alagapachettiar Government College of Engineering and Technology, Karaikudi, is an autonomous government institution established in the year 1952. It is situated in Karaikudi. In this Karaikudi College Road, we are having 12 institutions within the radius of 3 kilometers. Feel proud to say that the land of nearly 4 acres, sponsored by Dr. R.M. Alagapachettiar for the educational purposes. Now our institution working under Government of Tamil Nadu. In our college, we are having 5 different UG programs and 6 different PG programs. With the initiative of Dr. Batmanabhan, coordinator, and Professor Pradeep, co-coordinator, this ATAL FTP got selected and conducting this program. Our coordinator selected this wonderful topic. You know very well that to meet out the low demand, we are moving towards the renewable energy resources. In the renewable energy resources, mainly we are focusing on solar energy and wind energy. The solar energy is a DC. To merge with the DC with the AC, definitely we need a converter inverter. The inverter plays a major role in the power system. Utilize the solar generated power to the grid. We need to convert the power into power AC to DC as well as DC to AC. In this conversion, inverter plays a major role. Adding this inverter is must, but at the same time, we are facing various problems by adding this inverter. Major problem in the using the inverter is the stability. Hope you all will get a useful information through this faculty development programs. In our department, we are having various research laboratory, such as a smart grid lab, drives lab, IoT with this GPU. Our students are doing many projects under this with the help of this IoT lab. One of the project done by our student is drone project. There is name is autonomous navigation vehicle. The project got selected by ISRO. Feel proud to share with you. The power quality analyzer is available in our department. With the help of that, our student and faculty doing energy audit in various places. One of the project done by our students in the Karaikudi Government Hospital and Kottayur Primary Health Center. The work done by our students and faculty has been formed as a paper that is submitted to a national level contest. In this, our students got a first prize. Various research activities with the help of the Smart Grid Laboratory also going on in our institutions. I feel proud of you all. You got a chance to attend this FTP. Utilize this program. It will be more useful. In addition to that, we are having electric vehicle project with a cost of 14 lakhs. Then Tamil Nadu Skill Development Corporation sponsored 1.1 crore rupees to establish a incubation center in our institutions. At the same time, in our institution, we are having various research laboratories. At the same time, you can visit, at any time, you can visit our institutions. Various testing facilities are available in our institution. You are all welcome to our institution. Utilize these available resources and facilities. Best wishes to you all. Thank you.
Thank you, sir, for your warm and insightful words. To provide us with an overview of what this FTP holds for us in the coming days, I now invite Mr. V. Pradeep, Assistant Professor, Department of EEE ACGCET, to brief us about the Faculty Development Program.
Good evening, dear participants. I'm happy to welcome you all for this ATAL online 6-day FTP program on impact of inverter-based resources in the power systems. Dear participants, we have built and operate the power systems from the 19th century onwards. We have understand the dynamics of the power system with the conventional generations. We have understand and mastered the controlling techniques for the conventional-based systems. The fault behavior of the conventional generators are well known, and we can establish a well-established protection system for protecting pressure systems. Our system is undergoing a once-in-a-century transformation. We are integrating a huge amount of renewable energy into the system. This makes us to revisit each and every aspects of our power system. In the presence of the current scenario, the presence of the inverter-based resources, we need to revisit all these aspects, which form the central theme of this FTP. In order to give the comprehensive overview of the entire arena of this FTP, entire arena of this issue, we want to give the full spectrum of the topics that encompasses each and every area of this issue. We will start with introducing the control of the normal inverters. Then we will proceed with the controlling of the grid-tied inverters. Then we are going to look at the impact of these inverter controls on the system dynamic, control, operation, as well as the protective relay. Dear participants, we want to give you the introductions to the harmonic analysis of these inverter-based power plants. And also we are going to introduce this from the system study point of view. How to do the load flow fault analysis in the presence of these inverter-based resources. We will also throw some light on the controller interactions of these inverter controls on the power systems. We will also culminate this entire journey of learning the impact of inverter-based resources in the power systems by looking at the case studies. We are going to give the case study of the grid compliance study as well as a case study of the building and grid integration study of the solar power plant. In order to give this extensive knowledge, we have the invited resource persons from the various walks of this issue. We invited resource persons from the premier institution of India like NITs, NIT Trichy, IIITM Kanjipuram and PH Tech Coimbatore. Academia, resource person from the industry. We have the resource person from the Central Transmission Utility, Power Grid Corporation of India Limited. We have the resource person from the Power System Operation Corporation of India. Now it is a Grid India. We have the resource persons who is working in National Grid ET. We have the resource persons who are working in the renewables. We have some resource persons who are the member of the IEEE working group as well as the SICRI working groups. Dear participants, we invited different resource persons to give the different view of this issue from the different perspectives. I hope this will excite you as it excites us. Happy learning. Thank you.
Thank you, sir, for outlining the objectives and key aspects of this FDP.
Let us conclude the inauguration ceremony with National Anthem. We request all the participants to raise for National Anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
We will now proceed with our technical session starting at 6:30 p.m. Kindly stay connected and make the most of this learning opportunity. Thank you all and let's embark on this enriching journey together.
Good
Now I
evening,
request
everyone.
Arudra to give a brief introduction about our resource person. Arudra, are you online?
Yes, sir. Good evening, everyone. It is my great honor and privilege to introduce our esteemed chief guest, Mr. Sandeep Yadav, a distinguished professional in the field of power and energy. Mr. Sandeep Yadav is currently serving as Chief Manager at Power Grid Corporation of India Limited, a leading organization in the power transmission sector. With an impressive 14 years of experience in the industry, he has played a crucial role in the development, operation, and maintenance of India's electrical power infrastructure. Academically, Mr. Sandeep Yadav holds a Master of Technology in Power Systems from the prestigious Indian Institute of Technology, Delhi, and the Bachelor of Technology in Electrical Engineering from Aligarh Muslim University. His academic journey has been marked by excellence, securing top ranks and recognition for outstanding performances in both undergraduate and postgraduate studies. Throughout his career, Mr. Sandeep Yadav has contributed significantly to various projects and has been instrumental in driving innovations in power transmission and distribution. He has also led and participated in multiple projects focused on enhancing energy efficiency, grid stability, and renewable energy integration. Beyond professional achievements, Mr. Sandeep Yadav is deeply committed to knowledge sharing and mentoring young engineers, making him an inspiration for aspiring professionals in the energy sector. We are truly privileged to have him with us today. Please join me in extending a warm welcome to Mr. Sandeep Yadav.
Yes. Good evening,
Good evening,
everyone.
sir.
Good evening, sir.
So, can you hear me all right?
Yes, sir. We are hearing you, sir.
Okay. Thank you so much. So,
Shall
thank
we
you for
start,
that.
sir?
Yeah, I'm ready to start. No problem.
Yeah, okay. Thank you, sir.
So, thank you so much for that introduction, Arudra, and I invite you all, each and everyone, for this session on the impact of renewable energy systems in our power grid and how it is changing the way we control, the way we protect, and the way we run our power system in general. So I'll quickly share my screen. Let me know if you can see it, and then we can proceed from there. Okay.
Yes, sir. It is
Could you
visible,
please?
sir.
It's visible. Thank you. I'll just change the slides. If you let me know if it's changing. So I'm at the second slide where there is a conventional and an inverter-based resource. Can anyone confirm if you can see the
Yes,
slide
sir.
all right? Okay.
It is visible, sir. It is visible, sir.
Thank you. So, so we all know, I mean, power system consists of three major verticals, starting with generation, where the power which is generated in different forms, and then there is a transmission, where we take the power from where it is generated to the load center where it is consumed, be it industrial or residential. Now, as in the introduction, someone rightly said that for the past 150 years, we have been running the power system in a certain way. So it was mostly dominated by synchronous machines, wherein the power is generated using synchronously large rotating machines. And all these machines, they run in synchronism at a particular frequency. In our case, it is 50 hertz. There are some countries which runs at different frequencies, like 60 hertz, as in case of US, Middle East, some parts of Japan, and some other countries where we use 60 hertz as their regulating frequency. So all these systems, they run in synchronism. They have their own inertia because of the large rotating machines, which are there in the form of rotor. So if you look at a conventional source, the energy medium, which is usually steam generated from coal or gas, that runs a large rotating mass, which is the rotor, and that energy is transferred from the rotor. The kinetic energy is transferred from the rotor in the form of electromagnetics to the stator, the alternator winding. It is converted to electrical energy, and then all the generators which are connected in parallel feed the load. So technically, the machines have a large inertia in the form of the large rotating mass. Bigger the machine, the more mass the machine has, the higher is the inertia. So even if the machine the kinetic energy stops flowing from the input, the alternator can still provide for a few seconds the required amount of rated power. So that is why inertia is measured in the form of the unit is megawatt second. However, as we are moving towards more and more converter-based resources, also known as IBR, inverter-based resource, these machines, they do not have a large rotating mass. They are mostly in the form of these semiconductors, power semiconductors, and the electromagnetics is totally decoupled. The load is totally decoupled from the generation. So the dynamics that we have been seeing in the form of energy coming from one side to the other side, and it is coupled through an magnetic medium or electromagnetic medium, which is not the case in case of inverter-based resource. So both in terms of a steady state as well as in terms of dynamic state, they are very different from the conventional sources. So this is how a conventional source reacts to a change, a perturbation, or a contingency. So for example, there is a rotor rotating at synchronous speed. It has its poles, and they are coupled with the electrical poles of the stator, from where we have this three-phase alternating waves which are displaced by 120 degrees. So a balanced three-phase wave is generated through this mechanism, and the conventional sources, they act like a strong voltage source. So when we say voltage source, it means that if you try to change the voltage, the machine resists the change in voltage. It can supply large amount of reactive power or a good amount of short circuit power whenever it meets any contingency. So whenever there is a terminal fault or any fault at the electrical terminals of the machine, because of the changes in the inductances, we see varying level of impedance. So initial for 1 or 2 cycles, the inductances or the impedance is known as subtransient impedance or subtransient reactance. So it is usually very small in nature, and that is why we see that the fault current that this generator feeds in the initial few cycles is much higher. And at the same time, depending upon at what point on wave the fault is happening, the DC component will vary. So subtransient state the fault current is very high. After a few cycles, we have the transient state, or the system sees the transient reactance, which is slightly higher than the subtransient reactance, and that is why the fault current is lower. And then when the transient state passes, we have the steady state fault feeding condition, wherein we only have the steady state reactance of the machine, and the DC component or the DC offset also dies by this time. So we see three different states when it comes to feeding a fault by a conventional source. So it is easy to say that the conventional machines, they follow the rules of physics, and given the machine parameter and the physics of the machine, the construction of the machine, the inertia and the short circuit response of the machine can be easily assumed, or we can easily guide how the response of the machine will be. However, when it comes to a inverter-based resource or a converter-based resource, there is a decoupling in between. For example, these windmills, or the WTG as we call them, wind turbine generators, they generate an AC wave, and we may have, depending upon the machine, depending upon the design of the converter, we may have a diode rectifier which provides us. Sorry. So there may be a diode rectifier which provides us the required amount of DC voltage, and then we have a voltage source converter or voltage source inverter to convert that DC unipolar DC voltage into a three-phase voltage by switching the IGBT modules in a manner where it provides a steady state 120-degree displaced positive sequence voltage. So when you see that the output of the voltage source converter, it kind of decoupled from the input of the machine. So depending upon the control algorithm, depending upon the way we switch these inverters, that decide what kind of fault current it will feed, what kind of short circuit response it will have. And so, for example, this is the case of a phase-to-phase fault in R2Y phases. So a phase-to-phase fault, if it happens, it is very safe to assume that the synchronous machine will feed a fault wherein the fault current in R phase will be 180-degree opposite from the Y phase. So R and Y, both the phases will have 180-degree phase shift, and the B phase will be more or less depending upon the grounding of the system, because it is usually solidly grounded. The B phase will be largely unaffected. So all the synchronous machines, whatever their size is, whatever their machine parameters are, they behave, their short circuit response is identical. I mean, they behave almost the same way, which is easily predictable. However, in case of inverter-based resource, it could be very different depending upon the type of control algorithm, the type of voltage ride through that a particular original equipment manufacturer or the OEM, which is the manufacturer of the inverter, has built in its voltage source converter. So the short circuit response of one manufacturer may considerably vary from another manufacturer, given the type of control algorithm that has been used. So it is difficult to predict the type of response that we are going to get from an voltage source converter or an IBR, and that is why we, as a utility, have grid codes in place. So the grid code of any utility or any country, it binds the generators or the IPPs or the individual power producers to follow a certain regulation in terms of how the steady state and fault behavior of these machines will be. What will be the ride-through requirements, both in terms of low voltage and high voltage, and what will be the how much reactive power it will consume or at what power factor it will run. So all of these things are defined in the grid codes, and all the utilities, the generators which are connected at the grid point or the point of connection or point of interaction, point of interconnection, sorry, and all these IPPs, all these generators are bound to follow that grid code. So every country, we have these grid codes in place, and when the generator is connected for the first time, all these requirements are checked through the models as well as at the site. So at the first time interconnection or when the first time energization clearance is given, all these requirements are verified. So we had the comparison of a synchronous machine with an inverter-based resource. We can see that in terms of short circuit response, we know that the conventional generator will have a universal short circuit response. It is predictable in nature. More or less, it will be same for all the machines. However, the short circuit response of a inverter-based resource may vary from manufacturer to manufacturer. The short circuit current in a conventional generator may be the multiple times of its rated current. It may go up to 6 to 10 times of the rated current of the machine. However, in case of inverter-based resource, by virtue of using current limited devices like the semiconductors, usually in the form of IGBTs, their short circuit current is usually rated 1.2 or 1.3 per unit of the rated current. So there is a huge difference when it comes to the fault response of a conventional or an IBR generator. When it comes to feeding the negative sequence current, so whenever there is an asymmetrical fault, a line to ground fault or a double line to ground fault, whenever there is an asymmetrical fault, the conventional generators, they can feed large negative sequence currents, and these are very important when it comes to protective relaying of transmission lines and other components in the system. However, in case of IBR, because they are current limited, first of all, and second, by virtue of their grounding and the rating of the DC link capacitor, the negative sequence current is usually limited by the controller because it cannot feed negative sequence current for sustained period of time, because that will require a very large DC link capacitor, which is against the very economics of the inverter-based resources. And later in the last, we have a predictability in terms of the phase angle between the voltage and current at the time of fault. So because the synchronous machines act as a voltage source behind reactance, the current that it feeds usually is lagging in nature when it is compared with the voltage. However, in case of a voltage source, in case of a inverter-based resource, the current the phase relationship between voltage and current could be anything depending upon the algorithm. So two physically similar machines, they exhibit similar short circuit responses in case of conventional sources. However, in case of inverter-based resources, two generators of different manufacturer, two inverters from different manufacturer may have very different or significantly different short circuit responses or short circuit behavior. So with this, when it comes to the reliability of the protection, all these protections, be it differential, ground fault protection, distance protection, or the impedance protection, all of these have been designed keeping the behavior of synchronous generators or the conventional sources in mind. So what would be the phase relationship between voltage and current when it feeds an inductive fault, a highly resistive fault? All those behaviors, they have defined and formulated the very basics of our protection algorithm in the conventional impedance relays or our distance relays. So because these relays, they have been developed and designed over the period of time, keeping these synchronous generators in mind, now that the fault behavior of these inverter-based resources has changed considerably from the conventional sources, the reliability of the distance protection, of the line protection, and other protection schemes in general needs to be looked into, and their reliability for all kinds of fault, for weak sources, for strong sources, grid side or the inverter side, they all need to be looked into to ensure that the fault is cleared in minimum duration and it is not prolonged for a long period of time. So the reliability of the line protection scheme, because they were designed for conventional resources, the reliability could be at risk when there is a transmission line which is solely supplied by an inverter-based resource. So for this fault near terminal 1, because the terminal 4, 3, and 2, they will see the fault current fed by the inverter-based resource. The impedance protection 21 at the terminal 2 will have a difficult time in terms of detecting the fault and clearing the fault. We'll see in the upcoming slides why. So this is a typical fault behavior of a type 4 wind turbine, which is a full converter scheme, not the type 3, which has DFIG, doubly fed induction generator, and where there are two mediums through which the power can go. Type 4 wind turbines, they are totally decoupled. The WTG is totally decoupled from the grid, and the converters are rated for the full rating of the machine. So if you look for an AB fault or for an R2Y fault, in the pre-fault state, there is only positive sequence voltage and positive sequence current in the normal healthy system. And at the point of fault inception, we could see that before the controller kicks in, so the period of the fault inception, and by the time the controller recognizes that there has been a fault and its fault response, the controller decides how much and in what sense the fault current will be injected. This period will be, because it is a phase-to-phase fault, will not have any zero sequence current. All we will have is positive and negative sequence. So for this brief period, we will see both positive and negative sequence current in the current, in the fault current. So both positive and negative. Now, as soon as the converter detects that there has been a fault and the current control of the inverter kicks in, we will see that the controller will try to suppress the negative sequence current, and from this second pink line to the third pink line, this is the transient state, transition state, from where the converter will try to suppress the negative sequence, and it will only supply positive sequence current. And so for a phase-to-phase fault, we see after a few cycles, we see that the inverter-based resource, they only supply positive sequence current. So in the upcoming slides, where we take the case studies from the real systems in the Indian grid, real faults, we will see that what is the behavior of the fault current or the inverter-based resource in case of face-to-face faults, or in case of face-to-ground faults, where we will see the zero sequence coming into play. So for a face-to-face fault, during steady states, after a few cycles, all we will see is the injection of positive sequence current only. And this positive sequence current will not be very different from the pre-fault current in terms of its magnitude. So it will be limited by the current limit of the IGBTs. So because those are current limited devices, and it will be at max, the maximum value could be 1.1 or 1.2 per unit of the rated current. So that is why the conventional relays, or for example, the distance relays, they have a difficult time detecting the fault, because the magnitude has not changed much. The current has not risen considerably, and at the same time, there is no negative sequence or zero sequence current to determine the directionality of the fault. So we'll have a closer look in the upcoming slides why. So let's take an example of the same example that we took a few slides back. For a R2Y fault, R2Y face-to-face fault here, we know that the response from the conventional source will be 180-degree opposite currents. And because it is a face-to-face fault, the zero sequence will be very, very little, or may not be there at all, because it is a face-to-face fault and there is no ground involved. So IR will be equal and opposite of IY. However, in case of inverter-based resource, in case of solar, the WTG wind farm, the total current fed will be positive sequence only, which will be very little different from the pre-fault currents. So for a face-to-face fault, we see that IR is equal to minus IY for conventional generator. However, IR, IY, and IB are almost balanced when it comes to the fault response of a wind farm. So, and the vector group of these transformers, the step-up transformers of these wind farms or the solar power plants, they also have a role to play, because we'll see in case of a single phase to ground fault. So we see that the response from the wind farm is only positive sequence, and there is no negative sequence current, or very little negative sequence current to play with, and that is why the conventional relays will find it difficult to determine the directionality of this fault. So there are chances of maloperation when it comes to operation of distance protection or the conventional line impedance protection. This is the case of a middle phase to ground fault, or a Y to ground fault. So if you look at the ground fault, we see that the response from a synchronous machine is the current in the faulty phase has risen from 1 per unit to 3 per units, and the current in the faulty phase has risen. However, the healthy phases, the current is still 1 per unit. If we look at the wind farm, because it is a asymmetrical fault, it is supposed to have positive, negative, and zero sequence current, and usually they all are. If you take example of a single phase to ground fault, you have I1, I2, and I0, all three sequence component, and they all are equal. So the fault current is usually 3 I0. So fault current in the faulty phases, I1 plus I2 plus I0, and because all three are equal, they become 3 I0. So if we look at the output of the fault response of the wind farm, we see that the negative sequence current is suppressed by the control system, as we saw in the case of face-to-face fault. So out of positive, negative, and zero sequence, the negative sequence has been suppressed by the controller, and all we get is this zero sequence current because of this delta winding. So we know that delta winding, if we have a delta winding in a transformer, it acts as a source of zero sequence current. So all we see is zero sequence current in the fault current, which is fed by the wind farm. So it will be same in all three phases. So although the fault is there in the Y phase, the current in all three phases is 1 per unit, and they all are in phase, because zero sequence, they all zero sequence components of fault current in all three phases are equal. So all three currents, they are equal and they are in the same phase. So it is largely a zero sequence current, and a relay which is based on negative sequence polarization will not be able to detect this fault. So we need a directional element which works on the basis of zero sequence current. So a directional element which operates on the basis of a zero sequence current will be able to detect this fault because it is largely zero sequence in nature. However, on the conventional source side, we have all three components in place: positive, negative, and zero sequence, right? So because the controller plays a very big role in defining what would be the fault current behavior, and because the legacy systems or the old systems do not support injection of negative sequence current, the fault response is very different from a conventional source, both in case of a single phase to ground fault as well as in case of face-to-face faults. So as the penetration of these renewable sources grow, there are multiple issues that are being faced by the system operators. A broad classification is there are power system stability issues, because these systems do not have any inertia. They do not provide any system strength. So these systems are kind of lighter in nature, and any contingency or small disturbance may lead to large changes in voltage. So and same goes with the frequency. The rate of fall of frequencies, which is also rate of change of frequency, also known as Rokoff. The rate of change of frequency is larger as compared to the conventional sources, and also the as the renewable penetration grows, the lowest frequency of the system, in the case of a fault, may also deepen. So in a strong system with the large synchronous machines, because they give inertial response, the fall of frequency may be lower as compared to the system with a high penetration of renewable sources. Then there are issues with that which are related with protection systems. We just talked about a few slides ago. There are power quality issues, because these devices are switched in nature and they produce considerably large amount of harmonics as compared to the conventional sources. So conventional sources, given the uniform distribution of the stator winding across the periphery of the stator, we have very little harmonics in the system, or close to zero harmonics in the synchronous machines. However, depending upon what kind of control algorithm the OEM has used, the harmonics could be very different from one manufacturer to another, and that is why the grid code specifies what would be the DC current injection, what would be the individual and total harmonic distortion at the point of interconnection. Then there are operation related issues we'll talk about briefly in the upcoming slides. And later we need to put some systems into place as far as the grid discipline is concerned. So recently the Indian Electricity Grid Code of 2023, it was updated, and it now encompasses a lot of different variety of requirements for as far as the operation and protection of the power systems are concerned. So this has nothing to do with technical, this particular slide. This is more about how the systems are managed in Indian system, the Indian context. So what is the role of RPC? What is the role of load dispatch center, and so on and so forth. So all these systems have been modified, keeping the changing system in mind, the changing power system in mind. So one of the recent resource for inverter-based resources is IEEE 2800, which defines various requirements of how the system should be connected to the bulk power system. How these generators, solar, wind, and other inverter-based resources shall be connected to the bulk power system. So, however, when it comes to protection, the IEEE 2800, it does not specify what kind of protection is to be used, and it still largely remains the responsibility, or the it is defined as per the requirements of the transmission system owner as to how the system should behave and what kind of protection is to be used. So anti-aliasing protection, the kind of protection which is to be used at the point of interconnection. So it is still the responsibility lies with the transmission system owner. Characteristic of fault response in case of inverter-based resource, we talked about it. The first period is the first arrow. If you see, this is the point when the fault has taken place, where the fault has been detected. For a few cycles, it is the short circuit current will depend on the sizing of the LCL filter and the DC link, the size of the capacitor in the DC link, how much current it can feed. So it can go up to, say, 2 per unit, depending upon the inverter rating. Once the controller kicks in, which is the second period, the converter suppresses the negative sequence current and try to ride through the fault as per the grid code. And the peak current could be slightly lower than the first period, and then the final, which is the third period, where we have only the steady state, and which is in case of phase to phase fault, it is mostly positive sequence, and in case of phase to ground fault, it is usually zero sequence at the point of interconnection. Challenges with distance protection, we talked about it. The impedance which is seen by the relays, it depends upon the control strategies of the OEM. So the current injection with respect to voltage, it may vary with the control strategy, and that is why the impedance which is seen into the system by the distance relays, it also varies considerably, right? So it may so happen because as we saw in the last slide, the fault behavior, the current injection is changing with time in the first period, second period, and the last period. The impedance seen by the distance element, phase distance element of distance relays, it may overreach or underreach or drop out totally because of the oscillating impedance seen by the relay. The usual polarization method. So we know that the relays are polarized in order to determine the direction of the fault, whether the fault is in forward direction or the reverse direction. There are polarization methods in place which work on the basis of phase relationship between current and voltage. And because in case of conventional sources, the current and voltage, they usually have a predictable phase relationship depending upon the grounding of the system, the unbalances in the system. They are largely predictable. So all these polarization methods, they struggle when it comes to determine the direction in case of fault current fed by the IBRs. And in the last the last point is that there is a large variation between the different phases of the fault current when it comes to IBR fault injection. So if the distance relays are finding it difficult to detect the fault, the usual go-to protection is differential protection, and by far differential protection work just fine in case of even in the case of fault currents as seen from the inverter-based resource. However, there are minor nuances which needs to be looked into. One of them is because the differential protection, it works on the basis of difference of currents at both the ends of the transmission line. For a fault which is fed by conventional sources from both the ends, the difference in both the currents will be different. And however, the IBR may have a different phase relationship, both the sending end current and the receiving end current, the phase difference will be different. And then we have differential relay, which is located on the side of the inverter-based resource, may find some difficulty when it comes to phase detection or the starting of the protection, the starting of the differential protection. And however, still, I mean, the differential protection is a no-brainer when it comes to apply it on a system which has a large penetration of inverter-based resource. It is way better than the conventional line impedance protections. So this was the basic theory. I mean, we all have been discussing about it for the past few years or all over a decade. What I really want to go is the case studies that we have seen in our system. So we see the first case study, it talks about the role of pickup to drop-off ratio in case of over voltage protection. The second one is the coordination of over voltage settings in different substations. And the last is what kind of fault contribution have we seen in the real system when it comes to renewable sources. So this is the initial days when this is a snapshot of a system in the western Rajasthan or in the northern part of India. So mostly if you see the substations, these are large pooling substations where more than 10 or 15 wind farms and solar generators are connected. So Badla, Fatehgarh, Badla 2, these are all pooling stations where more than 3,000, 4,000 megawatt is power, solar power is being pooled, and then later it is through these 765 kV lines, it is fed to the load centers. So so let's take an example of Y to B fault, a phase-to-phase fault on one of the 220 kV transmission lines directly feeding, which is connected to one of the solar generators. So a 300 megawatt solar generator is connected to the point of interconnection at the 220 kV bus of power grid, and there is a phase-to-phase fault in that transmission line, the 220 kV transmission line. So let's take a look at the behavior of the fault current which is fed from the grid side, from the where all the synchronous machines are connected. So on the grid side, and then we look at the fault current which is fed by the solar generator. So this is the snapshot of one of the disturbance record. So you take a look at, this is a Y to B fault, yellow phase to blue phase to phase fault. The total fault current is fed from the grid side is 22 kiloampere or 22,000 ampere. So 22 kiloampere fault current is fed from the grid side. And if you take a look at their phase angle, the Y phase, if you take the Y phase as reference, so it becomes 0 degrees. And the B phase is 179.7, or which is equal to 180 degrees. And also, if you look at these two phasors, the phasor 2 and phasor 3, which are nothing but Y phase and B phase currents, they are totally in phases opposition, which is expected from a synchronous source. So Y and B both are in phase opposition and both have the same, almost same 22 kiloampere fault current. And this is the fault contribution from the grid side. Now, the pre-fault current, the solar generator, it was carrying about 206 megawatt of power, close to 200 megawatts, and the corresponding current was 600 ampere. And the fault current has, the current from the grid side, it has risen from 600 amperes to 22,000 amps. However, on the other side, which is the solar generator side, the fault current is, it was earlier 600 amps, and now it is only 257 in Y phase and close to 174 in B phase. So, as we know that because these devices are current limited, the fault contribution is very, very small. It does not go beyond 1 per unit, which is the rating of the machine. So the fault contribution from, if you compare from the grid side, the fault contribution from the solar plant is almost negligible. So for these currents, for the current of this magnitude, 257 and 174, it is very difficult for the distance relay to operate, because there is not enough current to start the overcurrent element or the distance element of the distance protection. So, however, because the differential relays, they work on the principle of difference of current between the grid side and the inverter side, the difference would be 22 kiloamps minus 257 ampere. So there will be a large differential current, which will be seen by the differential protection, and it will work just fine. So you see at this digital input, as soon as it has detected the fault, it has issued the differential trip, and it has opened all 3 circuit breakers. So the idea was to show you the fault contribution from the grid side and the fault contribution from the solar plant side. Now, let's take a look at how the fault ride-through behavior of the fault ride-through behavior of the inverters has been. So the pre-fault current on the initial 3 channels are R, Y, B phase currents, and the bottom 3 channels are R, Y, B phase voltages. So in the pre-fault, the current was normal, about 794 ampere, and the fault current, the voltage was also normal. Now, as soon as the fault took place, what the inverters do is that in order to protect their inverters from possible damage from overcurrent, the current control loop inside the inverters, it reduces the current injection from the inverter. So what it does is that it reduces the active power drastically, and as per the grid code, what it should do is that it should provide reactive power to the system to support the voltage. So from 794 amps to it almost drops to 96 ampere, and then it slowly, if you see, it is slowly building up the current. And if you look at the time scale, even after 2.5 second, the current has not reached to its pre-fault level. So if you look at the Indian grid code, what it says is that in case of a fault, the grid code allows the generators to reduce their active power, but that active power should come back to 90% of the pre-fault power within 1 second. So if the pre-fault power is 300 megawatt, within 1 second of fault, it should come back to 90% of pre-fault power, which is 270 megawatt. So however, in this case, we can see that even after 2.5 or 3 seconds, the generator has not reached to its pre-fault power level, which is against the grid code, and it is not meeting the requirements of the grid code, this particular generator. And these are the early days, 2021, 2022. So what happens is that because all the generators, all the PV generators, they behave almost the same way. They all reduces its their own active power, and if all the PV generators, they reduce their active power, what happens is that the systems, all these 765 kV and 400 kV transmission lines, they become lightly loaded. And what happens when the transmission lines are lightly loaded, they generate more reactive power than they consume. So the voltage has, from 220 kV, the voltage has risen to 242 kV, and because of the drop in the active power, the voltage of the system has risen significantly. So if you look at the 765 kV level, the pre-fault voltage was 756 kV, which is close to the rated voltage of 765 kV. As soon as the fault took place, the voltage reached, because the power dropped, the active power dropped, and the system became lightly loaded, the voltage rose to 838 kV from 765 kV, and there is sustained over voltage because the active power is still low. The voltage is still, the over voltage is still sustained, and after 6 seconds or 5 seconds, which is the time delay for the over voltage protection, the over voltage protection operates after 5 seconds, and it trips the line. So this is the problem if the generators, they do not meet the grid code. So for example, if the active power comes back within 1 second, or if comes back to 90% of the pre-fault power within 1 second, the lines will be loaded again, and the voltage will fall down to somewhere close to the pre-fault voltage, and these trippings on over voltage would not happen. So one other problem was, what happens is that there is a term called pickup to drop off ratio. So for example, if the over voltage protection picks up at 100%, it will only drop off when the voltage goes down the level of 98%. So there is a 2% hysteresis in the system. So as soon as, if you look here, as soon as the voltage goes beyond the pickup of over voltage protection, because the drop off ratio is 98%, it does not reset. Even if the voltage comes below a certain level, If it is not below 98% of the pickup value, then the over voltage protection will not reset. So this was one of the problems in the early days. The manufacturer, the protection supplier was contacted, and they were discussed. The problem of the high pickup to drop off ratio was discussed with them, and they agreed to make changes to their firmware to bring it down to 99 or 99.25%. This was this is the case study 2, the same system that we talked about. There is a phase-to-phase fault on one of the 400 kV transmission line, and what was happening is that because whenever the fault took place, all these generators, be it WTGs or the PV generators, they all stopped their generation, or they reduced their generation drastically. All these 400 kV and 765 kV transmission lines, they get slightly loaded, and this over voltage situation, it persists for longer period of time, and as a result, these transmission line, they start tripping on over voltage protection one after another. So, and it causes a widespread blackout at the regional level. So this was one of the system. Most of these generators, PV and wind, they are connected to Fatehgarh 2. A lot of PV generation is connected to Badla, and all this power is coming down to the Fatehgarh station, and from Fatehgarh 2 to it is coming down to Badla 2, and from Badla 2 it is going to all other 765 kV substation to feed the load centers. Now, if the overvoltage strategy, the regional overvoltage strategy, is not planned properly, what will happen is that the outgoing lines, for example, this particular line, this carries from Fatehgarh 2 to Badla 2, this transmission line, it carries all the load which is coming from Fatehgarh 2 and Badla 2. So this is a very important link, and that is why the time delay for over voltage protection for this system should be much higher than the downstream transmission line. So the time delay for over voltage protection is, for these lines from Badla to Fatehgarh 2, is 12 seconds, and then there is a margin of 3 seconds for the more critical lines. So what happens if the transmission line from Fatehgarh 2 to Badla 2 trips? It will stop evacuating all the generation which is happening at Fatehgarh 2 and Badla. So what we did is that so this is what is happening, is that whenever there is a fault taking place, the voltage rises. If you look at this yellow line, the voltage rises steadily from the pre-fault voltage of 727 to 876 kV. So a rise of more than 100 kV, in the entire region, and this is because of the change in active power after fault. So the pre-fault current was over 1000 ampere, and it reduces as soon as the fault happens, and it comes down to 466 ampere. You can see the lack of system strength, because of lower number of synchronous machines connected in the Rajasthan area. What is happening is that the pre-fault voltage is in the range of 740 kV or at almost all substations, and the rise in voltage after fault recovery. So when the fault is gone, or the faulty line has been isolated, the change in voltage is significantly higher. So from 747, it becomes 851, 745 to 843. At Badla 2, from 751 to 828. So the rise in voltage, the step change in voltage is very high in case of weaker grids, because there is not enough system strength, or the short circuit ratio is very low. This is the a slide which captures the grading of over voltage protection in the entire area. So this was done previously. If you take a look at the pickup and time delays of the over voltage protection, they are slightly in the same range, you know. So the circuit 1 is 108% and 5 seconds. Circuit 2 is 109% and 6 seconds. So this is the over voltage grading. So if the voltage goes beyond 108% of the rated voltage and it stays for 5 seconds, the circuit 1 will be tripped. So there was not enough margin, you know, there was not enough grading between the circuits. So most of the circuits were graded like for 5 seconds, 6 seconds and 7 seconds only. So because there was not enough margin between the circuits in the entire region, whenever there was an over voltage condition, the circuit 1 will trip in 5 seconds, the other circuit will trip in 6 seconds, and then the other lines which are which have the time delay of 7 seconds, they all trip. So most of these transmission line within 7 seconds, they all start tripping one by one. What we did is that we implemented a much better grading strategy in the entire region, and you know, now what is happening is that the tripping times, the over voltage protection tripping times, they start from 5 seconds, and from 5, 6, 7, 8, they go up to as high as 15 seconds. So by that time, you know, because a few of the lightly loaded lines would have tripped, the transmission lines with higher delay will survive. So we increase the over voltage protection tripping time delay from the initial value of 6 or 7 seconds to in some cases 12 seconds, and in other cases 15 seconds. So after doing this, the possibility of the region-wide blackout was much lesser, you know. So let's take another example of the contribution, the fault contribution from renewable sources. So as we discussed a few slides back, I'm sorry, let's go back to the slide. Yes. So in case of face-to-face fault, we expect, what do we expect? From synchronous machines, the voltage will be, sorry, the currents will be equal and opposite in the faulty phases. And from the inverter-based resource, for a face-to-face fault, it will be only positive sequence. So let's verify it from a real-time or the real-time fault, or a real scenario in the system. So the initial 4 currents, R, Y, B, and this is the neutral. These are from the grid side, and the bottom 3, R, Y, B, these are the remote end, which is the solar plant end. Okay, so if you take a look, and this was a Y to B fault. So for a Y to B fault, if you take a look, the current in Y phase is 23 kiloampere with a phase angle of -163. And in B phase, again 23 kiloampere. So the current is in Y phase and B phase is same, 23 kiloampere, and the phase difference is also close to 180 degrees. So -163 and 16 degrees. So they are in phase opposition, Y and B. So the fault current is very high, 23 kiloampere, and they are in phase opposition, which is what we expected from the grid side. Now take a look at the solar plant side. So now if you take a look here, the magnitude of the currents is 151 amps, 277 amps, and 257 amps. So which is again very low when it is compared to the grid side. And if you take a look at their phase angles, the R phase is at 0, the Y phase is minus 122, and B phase is plus 122 or minus 240 degrees. So this is the positive sequence current. So, positive sequence is nothing but balanced R, Y, and B system. So if you take a look at these three red ones, which are the fault contribution from the solar plant, you see these red ones, they are equal in magnitude. The red phasors, they are equal in magnitude and they are displaced by 120 degree. So this is a positive sequence contribution only, as we predicted in the slides before this. So from the grid side, Y and B phases, they feed 23 kiloampere in phase opposition. However, from the solar plant side, the contribution is largely positive sequence and not more than the rated current of the inverters. So this is the difference. So these currents, they have large negative sequence. If you because this is a face-to-face fault, you will have a large negative sequence. However, on the solar plant side, in case of a face-to-face fault, we only have positive sequence contribution, right? Yes, this is the another example of a phase to ground fault. So let's go back to the slide for phase to ground fault. Yeah, this is a phase to ground fault. So in phase to ground fault, what will happen? The faulty phase, the current will be very high. If we look at the grid side, the faulty phase current will be higher. However, from the solar plant or the IBR side, all we would expect is zero sequence current. So all the three phases R, Y, and B will have same magnitude, almost same magnitude, and they will be in phase. Let's see. Yeah. So this is an example of a R phase to ground fault. So if you take a look at R phase, and this is the grid side, the initial three channels, R, Y, and B phase currents. The R phase current is 25 kiloampere. So this is the fault point where the dotted line is, and after fault, the fault contribution from the grid side in the faulty R phase is 25,000 ampere or the 25 kiloampere, which is expected. Now the voltage has dropped in the faulty phase. So the voltage has come down to 32 kV and the fault current is 25 kiloampere. Let's take, and this is the case of a fault current contribution from the grid side. Now let's take a look at the plant side, solar plant side. So this is the local end, which is the grid end, grid side end. The fault current is 25 kiloampere. And this is remote, which is the solar plant end. So if you take a look at remote end, R, Y, and B phase current, they are almost equal, 303, 268, and 291. So they are all almost equal, which is 300 amps. And if you just take a look at their phases, so 6 degrees, 0 degree, 13 degrees. So they're almost in phase. So equal magnitude of 300 amps, and the phase current is, or the phasor is also same. So if you take a look at these blue phasors, they're more or less in phase, which is the characteristic of zero sequence currents. So all we see in case of a phase to ground fault is relatively lower fault currents, and they're all in same phase. So all we see is a zero sequence current contribution from the solar plant side. Okay, so now these real life incidences, they corroborate the theory of the fault behavior from when it comes to the difference between a synchronous source and a non-conventional or a non-synchronous source. So the characteristic of the IBR plants or the non-synchronous sources is that the fault currents are not very high. They are more or less limited to their rated values, and the phase, the type of current, whether it will be positive sequence or the zero sequence, will depend upon what kind of fault is there. So for a phase-to-phase fault, it is largely positive sequence, and for phase to ground faults, it is only zero sequence. There is no negative sequence current contribution from the IBR sources. That is what we have established so far. Then there are other few observations. Let's take an example of line differential protection. Yes, so this is a fault, phase to ground fault in R phase. The fault current contribution from grid side is 26 kiloampere. The fault current from the IBR source is 300 amps, close to 300 ampere, and it is again zero sequence because it is a phase to ground fault. So fault contribution from the grid side is 26 kiloamp. The current contribution from the RE generator is only 300 amps, and it is in phase, so zero sequence only. Now, I know it will be difficult to read on a power plant on a virtual meeting, but let me guide you through this. The current contributions. This is from grid side. So again, 26 kiloampere in the faulty phase, which is R phase, and if you take the remote currents, it is again 300 amps, 318, 278, and 297. So we saw that the fault response of RE generator are significantly different than the synchronous generators. The current injected by the RE generator is considerably low, and it may depend on the converter control algorithm, and it may change from one manufacturer to another. Very limited negative sequence current injection, which also depends on the control algorithm from OEM to OEM. Then the relays, which are based on the memory polarization, they may face problems when it comes to detecting the direction of the fault. Relays which work on the basis of negative sequence polarization, they will also struggle. The negative sequence comparators of quad distance element, a quadrilateral distance element, will not operate at all because there is no negative sequence injection to work with. And there may be problems with the security and dependability of different zones in a line impedance protection. The frequency estimation algorithms of the numerical relay, they will also struggle when it comes to the contribution from the RE generator side. The problems will be faced in phasor estimation. Now, when we talk about the security and dependability, let's take a look at one of the example. So there is a line between terminals X and Y, Y is the strong source, which is nothing but a lot of synchronous generators acting in parallel, and the X is the current contribution from unconventional source, which is solar PV or wind or battery energy storage. So so for a relay which is located at the X terminal, the apparent impedance seen into the line would be the impedance of the line, which is M into Z line. M is nothing but the location of the fault. So if the fault is at, say, 50%, M becomes 0.5. If the fault is at 60%, then definitely from this point up until the fault point, the impedance will be 0.6 of the total, or the 60% of the total line length. So the total apparent impedance is M into Z lines plus RF is the fault resistance into 1 plus IY upon IX. So IY is the contribution from, or the remote in feed, the contribution from the remote end, and IX is the current seen at the relay terminal. So the apparent impedance is M into Z line plus RF, which is the fault resistance, and the current which is going into the fault is IX and IY. So IX plus IY. So now, if you take a look at this mathematical expression, IY upon IX. So because these are phasor quantities, IY and IX will have a magnitude and they will have a phase. Now, the phase difference between IY and IX will be considerably different, because IY is a contribution from grid side and IX is contribution from RE generator side. Sorry. So if you take a look at IY upon IX, there will be a ratio and there will be a phase difference, which will be angle of IY minus angle of IX. So because the way these two sources react to the fault, their phases will be very different. So if there is strong sources or the synchronous machines on both the ends of the transmission line, they will have same phases, same or slightly different phases. But because of the type of current in feeds from both the ends, the IY upon IX term could be very different. So if you take a look at the locus of this impedance from this point, this is the relay location. It goes from this point to up until the fault point, which is M into Z line, and then because this is RX plane, the fault resistance RF will be perpendicular, the parallel to the R axis or the resistive axis. So this is RF. Now, depending upon the expression IY by IX, this point could be anywhere on this trajectory. So depending upon how the controller will react to this fault, this point could oscillate and it could be anywhere on this periphery, and it depends upon the controller algorithm. The way the controller reacts to the fault, the way the short circuit response of this inverter based resources. Same goes with external. So this was an internal fault in the line. For an external fault, so this is the line from X to Y, and there is a different line, and this is an external fault to this line. Same, in this case also, the impedance would be the Z line, the complete line length, plus ZW, which is the impedance of this line, into IY by IX. So again, depending upon the type of current, the behavior of IY and IX, this point could be, the impedance seen by the relay could be anywhere on this dotted periphery. Now, because for example, the distance relays which are located here at the RE generator end, they do the magnitude that they see is very small. So IX is very small, right? So it may be very difficult for these distance relay to operate onto the fault. So if you take a look at this, this is the R, Y, and B phase currents, and this is the grid side. So the fault current in the Y phase, which is the faulty phase, is 12,000 ampere, 12 kiloampere, and the if you take a look at these digital channels, it says main 1 operated and main 2 operated, which are two relays which are used on the grid side. So both the main and backup relays at the grid side have operated because there is sufficiently large current in faulty phase, which is Y phase. So the fault current is 12 kiloampere, and both the relay which are located on the grid side have operated. However, on the RE generator side, for the same fault, the grid side is feeding 12 kiloampere. However, the RE generator end is feeding only 145 amps, 194 amps, and 54 amps. So these are very small currents. The magnitude is so small that the phase to ground loop of the distance relay, which is located on the RE generator side, will not pick up. So if you take a look at the digital channels of this relay, it has not operated, because there is not sufficient current at the time of the fault for the relay to detect the fault, right? So in this case, the relay has not operated. So grid side relay has operated on the left hand. However, the RE generator side relay has not operated at all. Now it comes down to if the distance relays are not the solution in case of RE generator ends, what options do we have? As we discussed in the beginning, line differential works good because it works on the principle of difference of the current. So even though the contribution from the RE generator end is not much, because the contribution from the grid side is large, the differential current will be high and the protection will always operate. So, and then there are different nuances, what kind of differential algorithm we should use. Should it be percentage biased? No, we will not go into too much detail into this because this is largely protection area, and we would like to keep our focus on the behavior of the protection itself and not into the algorithms that these relays have. So the percentage, I'll just say that the conventional percentage biased differential relays, they do not function that well as compared to the generalized alpha plane differential. So this is one of the algorithm. I would request you to just go through the text and see what's the difference between percentage bias differential and the generalized alpha plane differential. So the relays which employ this algorithm are better as compared to the percentage bias differential. There are other makeshift arrangements in the protection which can be used. So we can use carrier aided directional fault protection, weak in feed ecologic can be used, and time domain protections, they can also be used. Misoperation of over voltage protection, we just saw a few slides back that because of the low pickup to drop off ratio, which was 98%, the over voltage element picks up, but it does not drop off in time. As a result, the maloperation or the misoperation of over voltage protection takes place. So this was changed. there is one more challenge which comes when we coordinate the earth fault protection. So you know that these are backup protections and they work on the basis of they are inverse definite minimum time curves, IDMT as they are called. So the plug setting multiplier.
Sir,
And-
excuse me, sir.
Yeah, please.
Sorry for the interruption, sir.
No, it's okay.
If you want, you can take a break or you can continue if you want.
I think we are just 2 slides short of this presentation, and then I'll just conclude. So
Sure, sir. Sure, sir.
So I think we should close this, and we'll be through this presentation. Okay.
Sure, sir. Sure, sir.
This
Okay, sir. You can proceed. Thank you, sir.
Thank you. This is a penultimate slide. So directional earth fault protection. It is a IDMT based curve. So we have to set the plug setting multiplier and time setting multiplier. So when we try to calculate the operating time, the formula is for the standard inverse curve, the formula is 0.4 into time multiplier setting divided by I fault, which is the fault current, upon I set, which is the pickup current of the relay, to the power 0.02 minus 1. So in this case, if when we calculate the time multiplier setting, the I fault upon I set is the mathematical expression which needs some looking into. So in case of synchronous generator, what happens is that because the fault current is very high and it is much more than the rated current, the I fault upon I set term is greater than 1. So anything which is greater than 1 raised to the power 0.02 will be more than 1. So TMS will be positive. You get my point. So in case of RE sources, what happens is that because the fault contribution is not more than the rated current, so if your setting of the relay is more than the I fault, this term becomes less than 1, and less than 1 raised to the power 0.02, the entire term becomes less than 1. So if we subtract 1 from a term which is less than 1, this becomes negative. So TMS becomes negative. Now the problem is that the distance, all kinds of these numerical relays, or for that matter even electromechanical relays, you cannot set a negative TMS, because negative TMS does not make sense physically. So time cannot be negative. Distance time can only be positive. So because of this problem, it is very difficult to set the these earth fault relays or the backup earth fault relays in case of RE generator end. So this is one of the challenges. So what we do is that we keep the minimum fault current which is there on the which is available on the relay. So in this case, this is 0.025, and we just leave it to that. Okay. So thank you so much. That was all from my side. The floor is open to questions. If anyone has got any question, I'm more than happy to answer. Thank you.
Participants can ask questions if they have. Enable panel.
Hello, sir.
Yes.
Sir, can you please share these slides, sir?
Yeah.
Hello, sir.
I'll hand it over to I'll hand it over these slides to the moderator, and then from there you can circulate it.
Okay, sir. Thank
Yeah.
you.
So thank you very much.
After the session is over, we will send all the slides to the participants. If any of the participant is about to ask questions, you can ask.
Sir, good evening, sir. Actually, it was a very excellent presentation, sir. Sir, I have one doubt, sir. During the fault, during each cycle of the fault, we have the different control aspects. During first cycle, we have a different positive sequence and negative sequence combination. And the second cycle, the control algorithm will change according to the grid components. And the steady state, we have a somewhat different. We do not have any negative sequence current in the steady state. During which of these state our relays will take decisions, sir?
Now, yeah, that is a very good question. So if you take example of the fastest distance protection relays that we have these days, they need to, they operate in the range of about 25 to 30 millisecond, for the instantaneous faults. So for example, zone 1 is set instantaneous, there is no time delay. So it takes about 25 to 30 milliseconds. So that is your how many cycles? It becomes 1.5 cycle or 2 cycles at max. So, but because the amplitude of the current is very small, we saw that it does not go beyond 300, 400 amps, which is not even the rated current of these IGBTs. So the distance relays, the overcurrent element or the pickup element of these distance relay does not even start for that amount of current. So if you take a look at the algorithm of any distance protection, it needs to fulfill certain criteria. For example, there should be a considerable amount of unbalanced current or pickup current. So the faulty phase should have some threshold of current. Second is there should be a drop in voltage, which is there, and the relay should be able to determine the directionality depending upon what kind of polarization algorithm has been used, whether it is positive sequence polarization, memory polarization, or negative sequence polarization. So based on the directional determination, fault detection, these 2-3 elements, then the relay will decide to trip. Now all these things, they take a minimum number of samples for the relay to accurately determine the condition. So for example, some relays take a minimum 5 to 7 samples, some take more. So that is why these relays, they take about 1 or 2 cycles to clear the fault. However, because the current in feed from the RE generator side is less than the rated value, these elements do not pick up at all, especially in case of distance protection. So the distance protection, it works on the principle of apparent impedance seen at the relay location, which is nothing but voltage upon current. So impedance is voltage upon current, and because the current does not rise much, the impedance does not fall less than the setting of the zone. For example, zone 1, zone 2, and zone 3, which are different quadrilateral zones, because the denominator current V upon I, the current does not rise much, the impedance does not fall below the threshold, and that is why the fault is not detected by most of these distance relays at RE generator end. However, at the grid side, we see large infeed from the grid in several kiloamperes, and that is why the distance protection at the grid side will operate. But the distance protections which are installed at the RE generator ends, they struggle to operate. However, the differential protection, which exchanges information from one end to another and works on the principle of difference of current at both the terminals of the line, they operate at both the ends. So nowadays, what we are doing is that we are going for two differential protections, both main 1 and main 2, both are differential protection for the transmission lines which are directly connected to these solar or wind power plants. I hope that answers your question.
Thank you, sir. Sir, one of our participants have raised a question in our chat box, sir. I will read this for you, sir. Can artificial intelligence and machine learning improve inverter fault detection? From Dr. R. Saravanan, sir.
I mean, of course, I mean, if see, the problem lies in the very basics of fault detection. So because the behavior of IBR fault injection, the fault current injection of IBR is very different from the synchronous machines. As long as we do not alter or change the algorithms of these protection relays, which were primarily designed for the synchronous sources or the conventional sources. So all of these algorithms that we see within these protection relays, they were designed and developed keeping synchronous machines in mind. High fault current, a predictable phase relationship between current and voltage. All those things, which were typical of a synchronous machine, they were captured in the algorithms of the distance relay, these protection relays, and that is why they have been operating just fine so far. However, with more and more renewable sources being added, these relays are struggling because the behavior is very different from the synchronous machines. So if there are relays, which employ these artificial intelligence techniques or machine learning, they have to capture the behavior of the fault current. So if they are able to detect these fault, if they're able to identify these fault, they'll be able to clear the fault. So that is where the problems comes in. Thank you.
Sir, good evening. Sir, we have one more question in the chat box, sir. From Mr. T.R. Karthik Sandhu, sir. How near are we to the stage of tracking faults before they occur? Do you think it will be possible, especially with the advent of AI and AGI?
So see, I mean, what protections do is that they detect the fault only after it has taken place. So there is because all these relays, they work on the basis of parameters, electrical parameters, current and voltage, and they see sudden changes in current and voltages. So current rises, voltage drops is an indication of a fault. So until the fault has taken place, a relay cannot detect a fault. All it can do is that it can detect the fault in minimum possible period of time, depending upon what kind of how fast the detection algorithm is. But there is no way to detect a fault before it takes place. I remember there are these fault locators based on traveling wave fronts. So whenever there is a fault, the traveling waves are generated and they travel from the fault point to the different ends of the line. So whenever there is a fault in the line, the traveling waves, they are generated at the fault point and they travel towards the two line ends. Now, there is one manufacturer, or there are certain manufacturers which claim that because before the fault, there may be low energy discharges happening at the fault location. So a fault is nothing but a high energy discharge. So what happens that the medium ionizes between the transmission line and the earth, or between two conductors of the transmission line, and there is a high energy discharge which is nothing but a fault. So there are some manufacturers who claim that they keep looking for these low energy discharges, which are an indicator of a incipient fault or a developing fault. So using traveling wavefront detection algorithms, it is to some extent possible to predict the fault. But the protection relays in general, they only act after the fault has taken place. The other question from Akilan is it possible to use GPU in real-time controller implementation, or just for training the controller? No, I mean, see, the controller doesn't need training as such, because what kind of requirements are there in the grid code, and you only need to act accordingly to the grid code. So for example, if the grid code says that in case of fault, the RE generator or the inverter should ride through the fault. They should not get disconnected. So this is one of the requirements of the grid code, for example. So the OEM who is designing their controller, they know the requirement, and they know that the grid code says that for voltages up to 15% of the rated voltage, I should not disconnect my generator from the grid in case of a fault. However, if the voltage goes below 15% or 0.15 per unit, the grid code allows me to disconnect my generator or trip my generator. Okay, so because the specifications or the requirements of the grid code are very clear and precise, the controller can be programmed, the algorithm can be written in line with the requirements of the grid code. It will work just fine. So you don't need a lot of data or big data to train your controller, because it is not trying to estimate something. It knows what it has to do, and the requirements are very clear and precise. So the designers, they read the grid code, and they design their inverter controller accordingly. In the case study, the over voltage was 850 kV for 6 seconds. That seems too long. What kind of impact it creates in the power system? So, see, the over voltages, what happens is that they put dielectric stress on the equipment which are connected. So for example, if you have transmission lines, you have bay equipment, CT, CVTs, bus post insulators, surge arresters, transformers. So all of these equipments, because the voltage of the entire network rises, all of these equipments which are connected in shunt or series, they are subjected to these over voltages. But because all of these transmission equipment, they are designed to operate at higher voltages for a certain period of time, they have these temporarily over voltage withstand. They can withstand these over voltage for a certain period of time. So for example, if you take any the specification of any equipment, any bay equipment, it says that the bay equipment, for example, CT or a CVT or a surge arrestor, should be able to withstand, say for example, 1.5 per unit over voltage for 1 minute. So if the specification are, for example, for 1 minute, it can definitely survive for 6 seconds. So although these over voltages, they stress the insulation of these equipment, and which is not desirable, but they can withstand this for a short period of time. Where can we get load flow for stability studies? Load flow data. I mean, if you are asking for a PSSE model, Grid India or the POSOCO, they usually, and the CTU, Central Transmission Utility, they do these kind of load flow and contingency studies. So I'm not sure if they can share the data with you, but if there'll be a session from one of the member from POSOCO or Grid India, you can put forward this question to them, and maybe they can help you out.
Participants, if you have any questions, you can unmute your mic and you can also speak to the speaker. Uma Maheshwari ma'am has raised your hand. You can speak or you can type your questions in the chat box. Sir, myself, I also have one more doubt, sir. I have read
please.
many IEEE transactions. They have show the data of power grid that real-time fault has occurred here, and we have devised a system to overcome that. Where to get that kind of data, sir, to research with it?
So, I mean, if you want data, the best source of data is Grid India, because they have all the models, they have the line parameters, machine parameters, for example, and they have all kind of models with them. So you can collaborate with them. If you intend to write some transaction or a conference paper, you can collaborate with them, and with your skill set and their data library, you can come up with a good paper. So these we do have in PowerGrid and in CTU, we have the models available for, usually these are mostly, these studies are done in PSSE, so we have PSSE models, but you can write officially to any of us to collaborate and for research purposes. That should be okay, I think.
Thank you so much, sir.
Thank you. There's one
more
question.
question we are having in the chat box, sir.
Yeah, it says, since IBR faults are new to us, will the IBR power plants are given relaxation on penalty for violating grid codes? No, they're not allowed to violate grid codes at all. So the idea is that their models are tested before allowing them to connect to the grid, and all the grid, they need to strictly meet the grid code requirements before they connect to the grid. So they submit all kinds of modeling studies, third-party lab reports, where they establish these ride-through, low voltage ride-through, high voltage ride-through, and all kinds of requirements which are established in the grid code. So all the generators who intend to connect their generator to the grid, they must meet the grid code which is there in place. There is no relaxation as far as grid code is concerned.
Any other questions from the participant side? Sir, actually, most of the participants are teachers, sir, working as assistant professor or professor of various grades in different academic institutions. We do not have any courses or any introduction to PSSE in our curriculum, sir. Actually, we do have power system simulation lab where we introduce simulations using MATLAB, and in our institutions we have a licensed PSCAD as well. Is there any mandatory requirement to introduce PSCs so that
no, there's no mandatory requirement. In fact, PSCAD gives you much better dynamic performance than PSSE. So PSCAD, you can do EMT studies in PSCAT, but you cannot do EMT studies in PSSE. So PSCAT is rather better. I mean, in my opinion, it is a much refined software than PSSE. So, and if I'm correct, I'm not a modeling person, so I do not have a comprehensive knowledge of modeling. But as far as I know, PSSE files can be imported into PSCAT. I'm not sure. I need to confirm it with the modeling team, but I think you can use the PSSE file and can convert it into can import it into PSSE or Power Factory.
Thank you, sir. Sir, one more question. Actually, we are having a syllabus of power system analysis, power system operation and control. We are teaching power system protection. All we focused on the conventional based generations. Do we need to modify these syllabus in order to accommodate this?
See, these things are relatively new, not relatively new. I mean, they have been in operation for past 15, 20 years now. In India, they have been in operation since over a decade now. So slowly, because as more and more research is going into this, there are books which are being written on these subjects. However, as far as the protection goes, there is very little literature which is available in the market, even in the Western countries. There are very few, because this is still a very niche field. There is not enough conclusive text which is available on these things. But mostly, these are available in IEEE transaction papers, conference papers, or different conferences. But I think as the time progresses, there will be a need of introducing more and more content on these subjects in our textbooks and in our courses. But I am pretty sure that there is very little, even in the universities abroad. There are specific courses. For example, there are courses such as future power systems. There are some courses which are solely dedicated for renewable energy systems. But as far as the basic power system analysis goes in electrical engineering, all of us are still or even the best institutes in India, they're teaching the same power system analysis, Granger and Stevenson, Nagarath and Kothari, and all those books. So definitely, as the time progresses, there'll be a demand, and we will need to modify our textbooks and our course content to make it more accessible for the students and to make them aware.
Sure, sir. Thank you, sir. We have two more questions in the chat box.
Is there any role for PMUs to play? Yeah, of course. I mean, all this data, that you see, it comes from PMUs only, because the one which I showed, it was from the disturbance records of disturbance record of protective relays. So, but the data which is used for analysis and for state estimation, for contingency studies, and for taking decisions, which generators to take out, which generators to take in, which line to open in case of over voltage and everything. So the people, the system operator, which is nothing but Grid India, the system operator, they use PMUs as a reliable source of PMUs are like the eyes of system operator when it comes to the network. So PMUs, they play a very critical role in operation as well as analysis of disturbances. So if you take all the studies, all the decisions which are being taken, they are being taken based on the data which is available from the PMUs, because the SCADA data, because it's not time synced, so there is not much use of this data when it comes to analysis of contingencies or disturbances. So PMUs across a big wide area, all the samples which we receive from PMUs, they're all GPS time synced, so they can all be used for state estimation and disturbance analysis. So all of these PMUs, as per the new PMU philosophy, they are everywhere. They are to be connected at all 400 kV transmission lines. PMUs must be installed at all HVDC stations, STATCOMs, and all generators up to 220. All 220 kV lines connected to generators. So 400 kV, 220 kV, all the lines have PMUs now. Any line which is connected or charged, any additional line, new line, it must have a PMU nowadays.
Sir, in this question, in the continuation of this question, sir, what is the status of the PMU deployment in India, sir?
No, if there was a scheme launched soon after the grid failure of 2012. It is known as URSTDM. You can go to the site of go to Power Grid site or Grid India site, and you'll find URSTDM, which is Unified Real Time TDSM, Unified Real Time Dynamic State Measurement. So there was this scheme which was launched, and under URSTDM project, there were about 1,800, close to 2,000 PMUs which were installed, and then in the first and second phases, and it's still, it is a continuous scheme, and all the new lines which are coming, they are coming with PMUs. There's one question, but the reactive power pickup kind of situation will be faced for the first time, sir. How can they not be given relaxation? No, there's no relaxation. It says that the relaxation is the requirement is that if there is a fault, for example, what happens in case of a synchronous generator? If there is a fault, the machine, it feeds a large amount of current. It does not trip itself. So if the fault stays, for example, 300, 400 millisecond before the protective relay clears the fault, all the synchronous generators, they remain connected, and they provide large reactive current to the system to support the voltage. Yes. In the same manner, because these RE generators, they cannot, inject large amount of current. The grid code says that at the time of fault, if the voltage goes less than 0.9 per unit voltage, the RE generator can drop its active power, but it has to bring back its active power within 1 second. So it allows you to, it gives you a margin of 1 second to reduce the active power, but it says that you have to bring it back in within 1 second. So this is what the grid code says. So the controller should be designed in such a way that in order to protect its inverter from damage, they can reduce the active power, but at the same time, it's the whole control algorithm should be fast enough to bring back the active power within 1 second. So there is no relaxation in that.
Thank you, sir. Umameshwari ma'am, she's keep on raising hand. You can unmute your mic and ask the question, ma'am. If you're not able to ask over mic, you can type your question in the chat box, ma'am.
Dr. K. Thirumal, sir, you have also unmuted your mic in the meanwhile. If you have any question, you can unmute and ask now.
Sir, one other question in the chat box, sir.
Whether is it convenient to use trial version of PSSE for UG projects? So if you use trial version, it gives you enough functionality to test your cases. If you want to inject, if you want to simulate any kind of fault or contingency, I think the trial version gives you that functionality, so it should be okay.
If there is no question, we shall wind up the session, participants. Sandeep Yadav, sir, shall we wind up the session, sir?
Yeah, I think so. I've spoken enough, and that was all from my side. And thank you so much for listening patiently. It was really an honor to be invited for this. And I'll drop my email ID in case you guys feel to ask anything. You can
Sure, sir.
send it through email, and I'll try to answer it.
Sure, sir. We will share all the details to the participants, sir.
Right.
Now I request Anuleka Pandey to give the vote of thanks.
Thank you, sir. Respected dignitaries, esteemed speakers, faculty members, dear participants, good evening to all. It is with great honor and privilege that I stand before you to deliver the vote of thanks at the conclusion of the first day of ATAL Faculty Development Program on the impact of inverter-based resources in power system. First and foremost, I would like to extend my sincere gratitude to AICTE Training and Learning Academy for organizing this 6-day FDP. I now take this opportunity to thank our distinguished speaker who has shared his expertise and knowledge with us. Mr. Sandeep Yadav, Chief Manager of Power Grid Corporation of India Limited. Thank you, sir, for your enlightening session on power system dynamics, operation, and protective relaying. Your in-depth knowledge has provided us with a strong foundation on power system, stability, and protection. I also extend my heartfelt appreciation to the organizing committee for their meticulous planning and execution, ensuring the seamless conduct of this FDP. A special thanks to the technical and support staff for their continuous assistance throughout the session. Lastly, I would like to thank all the participants for your enthusiastic involvement, active discussions, and keen interest in learning. Your engagement has truly enriched this program. Thank you all and have a wonderful evening.
Thank you so much.
Sir, one more minute, sir. I want to add a personal thank note in this regard. Actually, we find such a wonderful resource person, Sir Sandeep Yadav, sir, from the LinkedIn. When I scroll down the post he made it in the LinkedIn, I really inspired by his post. I just want to share this post. I have shared my screen with you. It is one of the wonderful LinkedIn page that I have ever come across. So if you have enough time, kindly go through the post he made, and the words he used to explain each and every post is extremely good, and I was deeply impressed by his post. If you are really curious about the electrical engineering, kindly go through his post and his papers. He also linked his papers in this LinkedIn post. Kindly go through it. You will find it will be useful for you. And the slides he has, I will show his LinkedIn page. This is the SaaS LinkedIn page. And also, if you have any interest, kindly go through it, and you will get a lot of the information which will be very helpful for you if you want to learn any new things for you. And SaaS, I want to say some special thing about SaaS slides. It is extremely good, and it shows how much effort he is made to bring this wonderful slides, and each and every point has clearly explained, and even the students at the BE level can able to understand such a complex topics. He meticulously covered each and every aspects of the protections. He does not simply cover a single type of the protections. He covered the whole area of the protections, starting from the distance protections, differential protections, over voltage protections, such an extensive and he covered each and every area, and that too he explained with the case study. It is one of the best presentations that I have listened in the recent past. I have searched through the YouTube and look for any such presentations. Thank you, sir. Thank you for giving such a wonderful presentation, and we will be very grateful for you, sir. Thank you, sir.
I appreciate it. Thank you so much.